All right, so this next problem is pretty cool. Okay, so what we're looking at is how many receptors do you need on a cell? And how does the number of receptors on a cell, there's a cell picture here, depend, how many receptors do you need to do good sensing of a biomolecule? Do you need to have the cell completely covered? Do you need to have some small density? And what kind of rates are we talking about here? So in this problem, we've now had equations to derive equations to maximize the rates and things. But here we have to combine a few things together. Here, the receptors, which are these little black dots on this picture of a cell, are treated as disks. So this would be related to the cylindrical problem that we did on a 2D cell surface. Okay, the cell itself is a sphere, and the cell itself, so this is a sphere, S-P-H-E-R-E, and let's say there are n receptors here of radius RR. So before we're looking at bimolecular interactions, assuming that the receptor was spherical and whatever binder was spherical, and then they would come into contact with each other and bind in bulk. But here it's a little different. So we have once the ligand's bound receptor, it can be endocytosed. It can be shuttled, signaling rafts, and other processes. But what, including formation of higher order complexes. But what about once a cell hits the cell and not a receptor? So only a fraction of a cell is covered by receptors. Okay, let's say we have n receptor disks. Receptor disks on our cell. Let's say n is somewhere between 1,000 and 1 million. Depends on the size of the cell, depends on the receptor. Let's say our cell is 10 micrometers in diameter. Okay? And let's say each receptor disk is approximately 2 nanometers. This means that there's only like a 5 times 10 to the minus 3% to 1% coverage. That means that well over 99% of the cell surface is not receptor. So how does this impact binding? How does this impact our understanding of the biology? And how would we do this? Well, like we did with efficiency, we looked at Carnot engines or the Carnot engine, these things that are the upper limits. So we're going to consider upper limits here of a cell completely covered by receptors. Okay, by receptors. And so when we have this, if it's then the whole cell is the receptor, and so then our upper limit rate would be 4 pi radius of the cell diffusion of the ligand. Okay. From our derivation that we did before, this is ligand diffusion. And this is the cell radius, which the whole cell now, if it's completely covered in receptors, the whole cell is actually one giant receptor. Now, if we go and look at the overall rate, 1 over k plus, we calculated the upper limit rate, but here we have an overall rate. And the way we look at this would be as a series of rates that kind of our resistance is. So as you have resistors in series, this is a similar type of thing. We have 4 pi dLRC. This is the diffusion portion of that overall rate. And then once you've found your way to the cell, plus 1 over Kr. This is the time it takes to bind once you find the cell, bind to receptor, once you're already to the cell. Okay, so there's a kind of two-step process here. A lot of reactions, you have a diffusion limit or a rate limiting step followed by a reaction step. So we're going to look at estimating Kr in cylindrical coordinates that we looked at before for diffusion of a drug in a blood vessel. Okay, so if we have a top-down view of this, a patch of this region, we would have these receptor discs that would be spaced out in some way, and then a side view of this, of one of those discs, would look something like this, where you have a region of this surface where you have this disc. And so on this disc, you'd have the concentration would equal 0 at Z equals 0 for your R that is within your radius of your receptor. So you'd have this R for these two conditions right here. For everywhere, R is between 0 and radius of your receptor. And everywhere else, like right here, would be no flux. So then you have this arrangement like so. So this requires two-dimensional cylindrical coordinates to solve. This becomes 1 over R partial by partial R partial CL. Well, actually, these are total derivatives. Let's do it at steady state. dCl, dr. No, even though, actually, sorry, I'm going to go back on that. Even though it's steady state, it's a multi-valued, independent variable function. So R partial CL partial R plus would have to have the terms here for the z direction. Del squared CL over del Z squared equals 0. And this is the ligand concentration. Okay, so we have two things happening here. We have the z direction above this, and we have these receptor discs embedded in a sheet with different boundary conditions everywhere. So this is the equation, and as z tends to infinity, the CL is going to be equal to some bulk concentration. At z equals 0, for R less than equal to radius of the receptor, CL will equal 0, and for z equals 0 for R greater than or equal to RR greater than, okay, we're going to have dCl dz equals 0. So we need to solve this equation now in order to do it, but we're not going to. I'm just going to give you the solution. This is actually called Weber's disk problem. So if you want to look up how to do it, look up Weber's disk problem, which is this two-dimensional reaction diffusion equation for what this looks like. What you end up with for the actual diffusion rate, so that we'll need later on, is that dCl dz at z equals 0 equals minus 2 dL CL0 divided by pi times square root of radius of receptor squared minus your current radius squared, all if it's in this interval 0 less than equal to R less than equal to RR. Okay. So what you need to do, though, is calculate this over the entire radius of the receptor and then add it all up. So you have to calculate this flux over the surface of your receptor. this is CL, dCl, dz at z equals 0 times 2 pi r dr for that integration equals k plus CL0, some rate. This is because the total flux times area equals rate. So all of this comes to like this. Then, once you do this for one receptor, you multiply by total number of receptors. Okay, so then you have K plus binding to N receptors. Okay. So this K plus binding is going to be equal to N times Kr plus, which equals N times 4 RR dl. Okay, which is what you get from the integral of that equation right there. This is the solution. So N receptors for RR dl becomes the solution to Weber's disk problem with N receptors. You don't have to know how to derive that. That's just a place that you can look for further information on your own. So 1 over K plus, the overall rate, is equal to the 1 over 4 pi RC dl plus 1 over K plus binding. Okay. Which we now have a calculation for. So if we substitute this in, rearrange this whole equation, we have K plus, okay, equals 4 pi dl r of the cell times n radius of the receptor divided by n radius of the receptor plus pi radius of the cell. This is a very cool equation. It might not look cool just yet, but it's a very cool equation. And you'll see why in a second. We can also derive a limit, K minus is equal to 3dl over rr squared. This is for the release. nrr divided by nrr plus pi rc. Okay. Now if we recall, K plus max, okay, occurs when n tends to infinity. Okay. What happens when n tends to infinity of this? You end up with infinity over infinity, which is equal to 4 pi dlrc. So this becomes the gold standard. This becomes the equivalent of the Carnot engine, the Carnot engine. So we can calculate things as K plus divided by K plus max. Okay, this is the max determined by coming into contact with the cell. So this is K plus over K plus max now is simply equal to n radius of the receptor. Let me make that first r larger. I already had the divided by. N r plus pi rc. Okay, so you can rearrange this even further by pulling n out, which equals to radius of the receptor over radius of the receptor plus pi radius of the cell divided by n. So let's do a quick calculation. Question: how many receptors are needed to achieve half maximal binding So we'd say 0.5 equals K plus divided by K plus max. Okay, that's the calculation we need to do. Let's suppose that we're back to this radius. The receptor equals 2 nanometers. Radius of the cell is equal to 10 micrometers. Half maximal rate. It's not that bad. That's pretty good. So what percentage of cell is receptor? Okay. So why don't we convert all of these into a micromolar length basis, and then do the math. You end up with N. You just substitute these numbers in to this equation right here and make that equal to 0.5. You find that N equals 115,700 receptors, or 0.06% covered. This is an incredibly low density of receptors needed to function as a good sensing unit. This is one of those cool things about biology at the small scale. This is the equivalent of you being the sensor for fresh homemade cookies, and you are standing by yourself in the middle of the football field of Ross-Ade Stadium, and there is a little amount of that scent coming in from across the street at Insomnia Cookies or something. This result is just pretty cool. You need a very little amount of receptor to make a very good cell sensor.